Hello, today is a quite nice day for me. I'm going to actually introduce you to one of the more important concepts that I have ever uploaded to my YouTube channel. So we're still in the introduction to Green's functions. But today we're going to speak about a special result that I consider of fundamental importance in the development of the theory of classical electrodynamics using Green functions, and in the theory of condensed matter using Green's functions as well. I'm going to write it in red so you just don't forget about it. It's called the Kramers Kronig relations. This is really important. So then we just saw with the Lorentz oscillator that we have derived from the, or using the restriction of causality, this susceptibility. So which is given by omega sub p squared divided by 4 pi summation over j of f sub j of sinc of lambda sub j t times some decay factor e to the minus gamma t divided by 2. Okay, then even though we derive this from the or using the restriction of causality, which says that the spectral representation of chi of t, which is chi of omega, will only have poles in the negative or in the lower complex plane. Nonetheless, we should impose causality by multiplying chi of t with a theta function. So really chi of t imposing causality is equal to omega p squared divided by 4 pi. So this summation over j of f sub j here, theta of t, sinc of lambda sub jt e to the minus gamma t divided by 2. So then you ask, okay, so why do we impose causality by locating the poles in the complex plane, in the lower complex plane, and not just by multiplying by a theta? That's a good question. And actually, even though if we multiply by this step function in such a way that generally our causalities are of the form chi of t equal to theta of t multiplied by the just very same causality chi of t. So even in this problem, the spectral representation of chi of t, which is chi of omega, should have poles in C minus, as we derived in our previous lecture. So then this has to follow, but then as a result of this imposition of causality, we can write chi of omega in the spectral domain as a convolution between theta of omega and, of course, chi of omega. Let's just find out what's theta of omega. So theta of omega is the integral from minus infinity to plus infinity of theta of t e to the I omega t dt. We introduce some convergence constant epsilon that tends to 0, and then we rewrite the integral in the following form: theta of t e to the I omega t e to the minus epsilon t dt. Okay, and then this allows us to write limit of epsilon that goes to 0, integral from minus infinity to plus infinity of theta of t e to the I omega plus I epsilon all t dt. And then, of course, since this is only one for values of t greater than 0, so what we'll end up with will be the limit of epsilon that tends to 0 of the integral from 0 to plus infinity of e to the I omega plus I epsilon t dt. And then so we solve for this and we write limit of epsilon that tends to 0, e to the I omega plus I epsilon t divided by I omega plus I epsilon between 0 and plus infinity. So then we will use another limit to account for the infinity limit here. So then this is equal to limit eta that tends to infinity, limit epsilon that tends to 0 of e to the I omega eta times e to the minus epsilon eta. So then the thing here, so then divide this by I omega plus I epsilon. So the thing here is that this exponential here decays quite fast, in the sense that this eta is very large. So then this decays very fast, and then when this decays, even though this epsilon is 0 or is near 0, but since this eta is very large, so this is a decaying exponential, and then that makes this identically equal to 0. Then if I replace in the other limit, then I subtract minus e to the I omega plus I epsilon everything times 0 divided by I omega plus I epsilon. This then gives 1. And then we have our answer, which is minus 1 divided by I omega plus I epsilon, or this is equal to I divided by omega plus I epsilon. So then this is what theta of E is. And then what we are left with is the following. So then if we multiply here and here, so they were left with minus 1 divided by I omega minus I squared, so minus epsilon, and this is nothing but 1 divided by epsilon minus I omega. And if I multiply both numerator and denominator by the same factor, which is the complex conjugate of this complex number, so this is e plus I omega, e minus I omega, multiply that, and we get e plus I omega divided by e squared plus omega squared. Yeah, so then I hope everybody is with me at the moment. And then so then here, so I forgot I have to carry out the limit. Sometimes I forgot to carry out the limit, but you have to always do it. So then this is actually limit of epsilon that tends to 0 of e plus I omega e squared plus omega squared. Okay, then here we just write theta of omega as, so the first one tends to 0, so let me see how we should do this, and we will do it. Let me figure that out. So then yes, so then let's write theta of omega equal to the limit of epsilon that tends to 0 of the real part, which is this, plus I, the imaginary part, which is this. Okay, so then by definition, delta of omega can be thought as 1 over pi limit of some small constant, let's say epsilon that tends to 0, e divided by e squared plus omega squared. Okay, this is some definition that we can use. So then by multiply this by pi here, and by dividing here by 1 over pi, so then all of this becomes pi delta of omega, okay? And then if this goes to 0, this one here, making use of the limit, then this becomes a principal value that is only valid when omega is different than 0. So then in that respect, theta of omega is equal to pi delta of omega plus I principal value of 1 over omega. This is always this only applies for omega different than 0, so then that's so principal value 1 divided by omega is equal to 1 over omega for omega different than 0. Okay, and now that we have theta, so then okay, so let me say it in this following way. So then in a more general way, principal value of omega is equal to the principal value of, or no, let's write it in an integral form. The more general definition that you can use for the principal value is the following thing that I'm going to write here. Principal value of the integral from a to b, yeah, of fx divided by x dx. So you just split this integral into an integral just from a until before 0 and from after, just from after 0 to b. So this is what that looks like. So this is the limit of epsilon that tends to 0, yeah, of this integral from a to minus epsilon fx divided by x dx plus the integral from plus epsilon to b fx dx divided by x. This is the more general definition of the principal, the principal integral, the Cauchy's principal value, and then we just go back to theta. Theta of omega is just equal to then pi delta omega plus I principal value of 1 over omega. This result is clue in the development of the result of Kramers and Kronig relations. Okay, so then now that we can move forward, then we just recall that after we have imposed causality on our susceptibility, we write the following form: theta of omega, chi of omega. Okay, so then what that means is that we're going to replace what we know about theta, and then we're going to proceed. So chi of omega is equal to 1 over 2 pi times pi delta of omega plus I, the principal value of 1 divided by omega, convolution with chi of omega. Okay, then what is that give us? So what that gives us is this goes with this pi, it gives us a half of delta of omega convolution with chi of omega. Here this is plus I divided by 2 pi, the principal value of 1 over omega convolution with chi of omega. Okay, now we're going to write these convolutions as integrals, as let's say one might expect. So then this is equal to 1/2 the integral over d of omega minus omega prime chi of omega prime d omega prime plus I divided by 2 pi, the principal value of 1 over omega convolution with chi of omega. This thing here is nothing but just chi of omega. So then this is equal to a half chi of omega plus I divided by 2 pi, principal value of 1 over omega, convolution of chi of omega. Okay, so then with that said, let's write then chi of omega is equal to half chi of omega plus I divided by 2 pi, principal value of 1 over omega, convolution with chi of omega. And then here we can just take this part and subtract it from the left and from the right, of course, and then we get the following. We get 1 half chi of omega is equal to I divided by 2 pi, the principal value of 1 over omega, convolution with chi of omega. What this gives is that chi of omega is then I divided by pi. So this how does this convolution look like actually? So that convolution, of course, take into account the principal value. That's very important. So then this is the principal value here of this integral. This is chi of omega prime, the omega prime, divided by omega minus omega prime. Okay, so then this is what we have. And as you can see, this we can more or less imagine that there will be some restrictions on chi of omega that we have to fulfill. And they will come from the fact that there's chi of omega is equal to chi of some integral of chi of omega for some other like frequencies at which chi omega is evaluated at. So then now say that to derive the so-called restrictions. Let's see how we're doing in time. 17, not so good, not so bad, but it's okay. So chi of omega can be written as a real part plus I chi some imaginary part. So then if we replace that upstairs, of course, so then we're going to end up with the following formula. So then we're going to say that chi real of omega plus I chi imaginary of omega, that's going to be equal to I divided by pi, principal value of chi of real of omega prime plus I chi imaginary of omega prime, all of this divided by omega minus omega prime with respect to the omega prime. So then from here we can derive the following. Chi real of omega is equal to what? This I here times this I here gives me a minus 1. So then I have minus 1 divided by pi, principal value of the integral of chi imaginary of omega prime, the omega prime, divided by omega minus omega prime. This is the first Kramers and Kronig relation. Now, then here, the imaginary part of that susceptibility will be equal just to 1 over pi, principal value of chi real of omega prime, the omega prime, like this. So then we have these two Kramers and Kronig relations, and then you can say, well done. so we're kind of good in time, but not really. I want to show you something else. We want to see some symmetry of chi real of omega and chi imaginary of omega with respect to omega. Okay? For such a task, what we're going to do is that we're going to write chi of omega as a Fourier series in the following way. So chi of omega is the integral from minus infinity to plus infinity of chi of tau times e to the I omega tau d tau, and this is nothing but the integral from minus infinity to plus infinity of chi of tau cosine of omega tau d tau plus I integral from minus infinity to plus infinity of chi of tau sine of omega tau d tau. Okay? Now, what happens here if I then take the conjugate of chi of omega? So what will happen is that then I will have this integral here, now minus omega tau d tau. This will be here, this will be the same, the real part will just be cosine of omega tau, because cosine is a even function there. So then cosine of minus omega is cosine of omega, so this is d tau. Now this is here, this will be truly a minus, the integral from minus infinity to plus infinity of chi of tau sine of omega tau d tau. Okay, so then what we can see here is that the real parts are the same. So then chi real of omega is equal to chi real conjugate of omega, and chi imaginary of omega is equal to minus chi imaginary star of omega. See? And the same apply if you just change the frequency. So then this thing here will be just equal to chi real of minus omega, and this will just be equal to minus chi imaginary of minus omega. So then this symmetry tells us that chi real of omega is even in omega, and chi imaginary of omega is odd in omega. Now, said that this is an important symmetry for just a simplification that we're going to make. What we're going to do is that we're going to deal with, let's deal with some transformation that I want to perform on the real part of chi of omega. So then chi real of omega, we said that it was equal to minus 1 over pi, the principal part of this integral of chi imaginary of omega prime, the omega prime divided by omega minus omega prime. Okay, then let's do the following thing. So let's write minus 1 over pi, principal part of this integral, and we're going to multiply here up and down by omega plus omega prime. So times chi of omega prime, the omega prime divided by omega minus omega prime times omega plus omega prime. Okay, so then what is this equal to? Minus 1 over pi principal value of this integral here of, here it says omega prime, chi I of omega prime, the omega prime divided by omega square minus omega prime square, yeah, and then this is minus omega divided by pi principal value of the integral minus infinity to plus infinity of chi of omega prime, the omega prime divided by omega prime minus divided by omega square minus omega prime square. From the symmetry that we derive here, we see that since chi imaginary of omega prime is odd, and what we have in the denominator is even, so then this integral is identically equal to 0, which leaves us with chi real of omega being as well minus 1 over pi, the principal integral from minus infinity to plus infinity of omega prime chi imaginary of omega prime, the omega prime, divided by omega square minus omega prime square. So then this is the another form to write the Kramers and Kronig relation, but now with a quadratic denominator. Yeah, so then and the very same we can do really for the imaginary part. So then let's do it just really quick. Time 27 minutes, not so good, not so bad, well, not so good. So then let's see, chi imaginary of omega is equal to 1 over pi principal value of the integral minus infinity to plus infinity, the omega prime chi real of omega prime, the omega prime, sorry, I put the omega prime twice, so this is divided by omega minus omega prime, and this is 1 over pi principal value of the integral from minus infinity to plus infinity of omega plus omega prime chi real of omega prime, the omega prime divided by omega square minus omega prime square. See, so then this is the same here, so we have omega divided by pi principal integral from minus infinity to plus infinity. We have here chi real of omega prime, the omega prime, omega square minus omega prime square, plus 1 over pi principal integral from minus infinity to plus infinity of omega prime chi real of omega prime, the omega prime divided by omega square minus omega prime square. So what we have here is that this integral is 0 because omega prime, which is linear and odd, is multiplying chi real of omega prime, which is even. That means that the product is odd and is divided by an even function in omega. And so what that means is that this integral is an integral over from minus infinity to infinity of an odd function is 0. In that case, then we write the Kramers and Kronig relation for chi imaginary of omega equal to omega divided by pi. Principal value of the integral from minus infinity to plus infinity of chi real of omega prime d omega prime divided by omega square minus omega prime square. So then this is the other form of Kramers-Kronig relation for the imaginary part of the susceptibility. This is for the real part of the susceptibility. And then like this, we have just derived these restrictions that are so important when we work with classical EM or with condensed matter physics and among other disciplines. And this is everything. So then I hope that you enjoy this video. This is I don't think you will find this with such a level of clarity just anywhere, maybe in some books, Jackson, I don't know. So I just wanted to show you how to do it, how to arrive there. And if you, of course, if you have any suggestions for content, then please just leave a message downstairs. And then thanks for watching, and see you in the video where we're going now in real detail in constructing the Green's functions for potential problems. Now talking about the wave equation. Then see you.